This is just showing you an example of DQN learning. And it's just playing game after game of Breakout. So this is I guess most of you have seen the game of Breakout, but you've got this paddle at the bottom that you're trying to control. And basically it's just left, right. That's the only movements of the joystick here for the most part. You do have to press a button to launch the ball, I believe, but otherwise it's just left, right. And the ball bounces according to pretty standard physics, and you're trying to hit it off the paddle and break up these balls. You get points for breaking these things up, and the system just starts from scratch. And it's very, very interesting to try to put yourself in the place of this agent that's learning to play the game, right? So you got to remember the agent has no idea that this is a ball. It doesn't see things like that at first. It just sees a grid of pixels. And so what's the dimensionality for those of you who use Atari all the time? Do you remember, Mohammed? Is it no, the size of the screen, is it like 64 by 64?
I don't know. I think it must be 64.
Yeah, usually there's a little pre-processing. You turn it to grayscale, and then you're learning. And I think this one here they're using the previous 4 frames. But if you put yourself in the place of the agent, when is it getting reward, right? And how many time steps go by before it gets a reward? So we know as a human that it's kind of bad for the ball to miss the paddle, right? So we see this, for example, in the beginning. It's moving around. It's nothing's really happening. I don't know where the ball is here. There we go. Oh, yeah. So it was pushing the button, and so it just sees the ball launch down. Is there any negative reward it gets when that ball goes off the screen, when it misses the ball? No. There's no negative reward. You get positive points for doing good things. Yes.
So to be clear, sorry, it's forgot my question.
How long it would take?
No, it was that one was looking at for reward. I'm sorry, I just completely spaced.
Yeah. So anyway, the reward is just based on the points, and if the points go up, you get +1. Points go down, you get -1. Points don't go down here. If you miss the ball 3 times, the game's over. But there's no so it's good to extend the reward. Oh, before you forget. Yes.
Yeah, I remember now. So when it's initialized, is it effectively just doing random inputs, or is it giving a standard out or input for the controls?
So you initialize the input's always the screen.
Mm-hmm.
And the output is just so here I'm not sure what they use. There's usually 2 versions where you have all 19 or 17 possible actions.
Mm-hmm.
Then there's also versions which most people use that just consider the actions that are actually useful in the game.
Mm-hmm.
So because there's a lot of actions here that are sort of equivalent, like pushing the button and moving left is equivalent to just moving left. So I think they're probably using the restricted action space here. It saves a lot of time because that's a lot less to explore.
And so are all actions equally likely, or does it?
In the beginning, it's hard to say. It's just an initial random network.
Okay.
The weights are randomly initialized, and you can't really tell the likelihood of the actions, but more or less you would expect it to be, if you generated many random networks, you would expect those random networks to have equally likely probabilities. So it looks fairly easy to us, but when you think about it, the ball's going down and it goes off the screen. You get no negative reward. You're not told that that's a bad thing. Right? The only way that you know that it's good to hit the ball is, well, you don't know this, but we know it because it extends the game and you can get more points. Right? So it's just bad to lose lives. But the agent doesn't see the notion of lives directly. What it must figure out eventually is that somehow, here it's figured that out. Like it's figured out how to hit the ball, but how does it do that the first time? Right? So somehow the ball hits the paddle, goes up, it takes multiple steps, right? So who knows how many steps go by, decision cycles go by while the ball is going up from the paddle, and you get a point, right? And so that's a big credit assignment problem. It has to figure out that, okay, this pixel configuration that I just saw sort of ended up causing that point that we got, 30 decision cycles later. Right? That's a lot of time, and that's why these things take a long time to learn. Right? So it has to figure out that correlation. There was a point, and I hit the it collided with this thing down here. And so eventually it does get some features that are powerful enough to recognize, wow. So we can actually watch the progression here. So it gets some features here. At least it knows now how to anticipate, where the ball is going to be. It misses sometimes. This is after 34 hours of training. And these are old results, so now training can be much faster. All right, so it's pretty good here, right? Humans are going to have a hard time playing at this speed. At least I would. And now pretty soon you're going to see this famous thing that they like to brag about. It shows that, that's sort of the breakout strategy. Try to get it on the top row. So it's pretty cool that it can actually learn to do this. I'm not really convinced that it really actively tries to get the ball to make a hole and go up to the top row like it does at the end. I think that might just be just an implicit thing that just happens if you play long enough, typically. But maybe its strategy did optimize to do that. But what we're thinking in your next assignment, you'll be doing this for Pong. So if you've ever seen, we can probably find Pong here. Pong, Atari. Try this. Right, Pong, Atari, and it gives you breakout. There we go. All right, this is going to be Pong with policy gradients. I guess they're showing you a learned policy. But this is an interesting one as well. And I want you to be thinking about this, because these things look really easy as a human. Like we know what paddles are, we know what balls are, we know, it's probably good to try to hit the ball with the paddle. But the green one's is the learning agent. Not terribly good right now and pretty erratic. But it's the same thing here. So if you think about what it has to learn in the beginning, it's just these pixels moving around. And when you do happen to hit the ball, you don't get positive points for hitting the ball, right? There's no score. You only get positive points when it gets by your opponent. You get negative points when it gets by you. So it's a really hard credit assignment problem. You have to somehow figure out that by putting your paddle in front of the ball, and whatever pattern that means, that causes the ball to bounce to the opponent's side, and you're more likely to get points than not, than to lose points. So as humans, we look at this and we're like, oh yeah, it's easy because we would imagine, you get a negative reward if you miss the ball, but you don't. I guess you do get a negative reward for missing the ball, but the reason for that negative reward is not at all clear, right? There could be lots of reasons that you got a negative reward. Maybe it was because you were down in the lower part of the screen and you moved up 3 times, and maybe it was because you were in the upper part of the screen. Maybe it had nothing to do with the ball. So these are hard problems, even though they look easy to us, and that's why it was kind of surprising to RL researchers that you could get Atari agents to play these games sort of just from pixel input, with no encoding features of the ball and paddle and the angle of the ball to the paddle, and so that's and so hopefully we'll be able to get you to get a Pong agent that plays in this next assignment. All right. Question.
Is the agent that was saying the breakout still work if I change the environment a little bit? Maybe have some random pattern of the blocks. Will it still play well?
Oh, hard to say. Yeah, I mean, it could completely fail. I mean, there are lots of. Here you go. They're always trying to sell me that thing. So, I mean, it is not unusual at all to see non-robust reinforcement learning agents that learn a strategy, and then you'll you might put, a colored dot here that a human would just ignore, and the thing will just wig out, right? So you don't really like these systems have no common sense. So they can definitely do things that look crazy to us. So they can look like they're playing brilliantly, and then you change something tiny about the game. Like maybe you just shuffle these colors around. And if it's looking at color, it could just completely wig out at that point. So, yeah, no guarantees. You would have to train it on the variations that you expect it to encounter in order and if it happens to generalize outside those variations, then you can consider yourself lucky, or maybe there is some inherent reason that it did generalize well. Yeah. So there you go. So back to the slides. I think we're just about done with DQN. So at the end of the day, you'll be implementing DQN, and it's like Q-learning, but with these other differences that we mentioned. The target network, that was an important one. Okay. There we go. Get rid of him. All right. So YouTube really wants to talk to us. Okay. So this is a good slide to refer to when you're implementing DQN, and we'll have some schemas for you. And then we've got these games. So these are ones that we train. So how long does it usually take you to train something for Pong, Mohammed? A couple hours on just your machine, or yeah. So you can train these a lot faster now. He's using an algorithm called A3C now, and we'll be learning about that. But there are other faster algorithms nowadays. Especially if you use concurrency, you can probably train Pong in. You can probably do it in like 15 minutes on the Dev Cloud if you use lots of resources. That's what Anurag was saying. All right, so we're pretty much done with this. So that at the end of the day, that's value function based RL with function approximation. And there's tons and tons of variants in the literature, but you could probably go out and pick up some papers and read them now and get through them. The first ones might take you a little while, but you've got all the vocabulary and the basic knowledge, I think, to read papers, and there's countless variations on all these things, and most of them aren't very important or critical, but there are some important variations. So any questions on function approximation? That part? All right. So now we're getting into another class of reinforcement learning algorithms that use function approximation. And this is a pretty popular class these days. It'll be interesting to see how the popularity between this and value-based methods evolves. I think there's good cases for both of them. I think there's a great case for algorithms that are off policy, like DQN and Q-learning, because you can just reuse experience. It doesn't matter how you collect it. Most policy gradient algorithms, most of them are going to be on policy, and that that's one little downside to them, but they've been showing pretty good results in robotics and other applications, and so they're pretty popular. Lots of new work coming out. So we're going to sort of start with the basics, and we'll then show you a couple of other more modern algorithms. Yeah, my personal experience has been policy gradient. Well, when it works, it's great, but when it's not, when it doesn't work, it's really hard to debug and get it to work. It's like I always use the term. It's like training a wild animal. You know, you tweak it a little bit, and it will just go over here, and you tweak it again, and it will go over here, and yeah, it's but when it works and you can tune it right, it can be pretty powerful. So let's see what we mean by policy search and policy gradient. So right now you've learned everything in terms of the idea was to learn a Q function or a value function. And we can use a Q function or a value function to define a policy using either just maximizing the action of the Q function or doing one step look ahead. Now, that's, those methods are pretty good, but there are some downsides to them. One is we talked about sort of theoretical stability of these value-based methods. Convergence is an issue when you have function approximation. So that's one downside, you could say. But still, they're widely used in practice. Another potential downside is that you can say that value functions might be representing too much information or more information than we need. Do we really care that the Q value for going left is 0.3554 versus going right is 0.533? We probably don't care about that. We really care about which one is larger, right, at the end of the day, if we're just using this to get a policy. And so learning the precise values of all the actions and all the states may be overkill in some sense. And it may also require that you have a more complex function approximation architecture than you would need to represent the policy itself. So the policy will always be simpler than a Q function. Right? So can anybody give me an argument of why the policy is is not going to be more complicated than a Q function? Anybody have intuition about that? Right, so if I use one type of neural network and it represents the Q values of all the actions, might I need a more complicated neural network to represent sort of the policy, just selecting the right action?
So the policy only needs to dictate what needs to be done at each state, whereas the Q function, the value function, needs to tell you what is the value of taking each action at every other state. So there's more, it's more complex.
So yeah. So the Q function must tell you, it gives you a real number for every action, right? It's going to give you a precise real number for every action. Whereas the policy, you can think of it as just giving a binary encoding, a binary output for each action, like 1 for the action you want and 0 for the others. Like that's one way to think about it. And that just requires representing the max of the Q function. So generally, Q functions are going to be more complicated to represent, or at least no less complicated than the policy. And you can sort of see that you can come up with domains where there are very simple policies. So let's think of a fictitious domain where it's a maze domain, and it happens that at every turn there's like a red arrow and a green arrow, and we're not told this beforehand, but the green arrow is always showing you the direction to move, right? So learning the Q values of the actions could be still quite complicated, but there's a policy that's very simple, which would just be, look for the green arrow and move in the direction of the green arrow. And that doesn't really capture anything about the domain dynamics. It's kind of a little cheat, right? And a lot of times in the environment, there are these little cheats that even if you, so maybe you started off by understanding the environment, but you eventually just learn, oh, I'm going to look for this little feature and then act in a certain way when I see that feature. So there's these very simple features that can tell you what to do, even though those features are not sufficient for predicting the future of either the state or the value. So that's sort of the main point there. And so these things might motivate trying to just directly learn policies, directly searching for policies and not bothering going through a value function learning step. And so how can we do that? So another motivation for policy search that comes up is when you have complex action spaces. So far we've been looking at action spaces that are just, there's 5 actions and you could learn a Q value for each of them. If you have a neural network, you could have an output node for each action. But in robotics, for example, you often have the actions are vectors, right? Real valued vectors where each component is, the power that you're going to send to an actuator. So that's a complicated space. You can't even enumerate it. So how would you learn a value function or a policy for that, or represent one, right? So, and likewise, there's also combinatorial action spaces where, think of it as you have a whole panel of buttons, and you can press subsets of the buttons at any time as your control actions. There are lots of domains like this as well. Those are combinatorial. The actions are effectively bit vectors. You can think of them as bit vectors, and any combination of assignment to the bit vector would be an action. And so again, there would be exponentially many actions in terms of the number of bits. And so, how would we represent a Q function for something like that? Right? Any ideas how we would do that? Right. How would we represent a Q function for a continuous action space? Let's say, so A is going to be a continuous action and S is a continuous state, we'll say, state vector.
You can write a function.
Mm-hmm. Yeah, so you could just say I'm going to have a Q function where the input is an action and the input is a state and it outputs just a value, right? So we saw with the DQN type of network, we had an output for every single action and the output was equal to the Q value. So we can't do that with a continuous case, but you could have a neural network, for example, that takes a state and the action as input. Even though they're numeric, that's fine, and outputs a single action. Now, what's going to be your challenge with actually using that Q function for control, like to actually run the robot? Well, is there a challenge there now? If we learn the Q function, what's the challenge? Finding the max, right? So now you have to find the maximum action in this continuous space. And you could do gradient descent, that sort of thing, but it's going to be time consuming and maybe inexact. So this is a problem, and people do take that approach, and they have various tricks, but it's a bit awkward sometimes. So yeah, so basically that's what this slide is saying. So instead, what you can do is you could just try to have a policy that directly outputs the action, right? You take the state as input and you output the action at the output. And so that's what this would look like. So the robot sensor history goes into a neural network. Maybe these are LiDAR sensors and video, who knows. And the output, you have a node for each of the N output action vector components. And it just directly outputs the action. Right? That makes a lot of sense. And then when you're actually running the robot, you can just call the neural net, you get your action, and there you go. And although, in practice, getting a large neural net to work efficiently on a robot can be a challenge in itself. You know, so, but but that's much more feasible than trying to optimize a queue function. Find the optimizing action of a queue function if you had learned it. All right, so and similarly, if you had bit vectors at the output, you could have a bit here for each possible bit vector of the action. So is that fairly clear? So I'd like to figure out, how do we actually learn something like this directly without going through a value function? All right, so just a reminder, we've talked about gradient descent before, but we're going to talk about gradient descent here because we're going to try to increase the value. And so this was just the idea that we have a function which has some parameters, and we want to maximize that function. So we're just going to move in the direction of the gradient. And we do that over and over. So we've seen this already. And this is just a picture. You start here in parameter space. The gradient says move here, then here, then here. And you can see the learning rate's kind of getting smaller as we go. You're going to hit this. And every time you run it, you might hit a different local optima. And that's why sometimes you do random restarts with these sorts of things. So that's gradient descent. And you can basically talk about policy search in a gradient descent framework. And that's a very common thing to do. So what we need to do is we need to select a space of parameterized policies. Right? So I just showed you one example of a neural network that if you change its weights, you're going to get a different policy, right, for every weight change. So the parameters are the weights of the neural network. Then what you're going to do is you need to be able to compute the gradient of the value of the current policy with respect to the parameters. So that's more complicated than just one line here. There's a lot packed in there, but if we could compute the gradient of the value of that policy, we would try to move in the direction of the gradient, and we would ideally increase the value of the policy, right, by changing the policy in a positive value direction, right? And you would just keep on trying to improve the policy that way until you couldn't improve anymore. Move the parameters in that direction, and you repeat until we reach a local optima. And then, of course, there's lots of tricks for trying to avoid bad local optima that people don't do so much these days, but yeah, they're good to be thinking about. So the main questions are, how do we represent policies, and how do we compute gradients? And I'm going to go through a basic linear policy representation first, and then we'll talk about neural networks as well. But linear, as I said, I like linear representations, and so let's start here. So one example, and this is a pretty common policy space. We're gonna be modifying this a bit, but this is just showing you some intuition. So this H function is going to be, I'm not using Q here. I'm using H because this is what we're going to call a scoring function. So it assigns a score to every action, which may or may not be equal to the value of that action. And you could represent a scoring function in a linear way, just like we represented a Q function, right? So you have some features, you have parameters, and for any parameter setting, for any state action pair, you get a score. And unlike the Q function, we're not going to require the score function to actually represent values. All we want it to do is, to be effective, we want it to be able to rank actions according to their goodness, right? So as long as it gets the ranking right, we don't care if it gets the precise values right, right? So that gives us some flexibility. It is sort of less constrained than if we're trying to learn a Q function. That can be good or bad, as we'll see. So let's focus on episodic learning for this episode, for this class. And So each episode will start from some initial state, S0, and it could be drawn from a state distribution as well. But a lot of these Atari games, you just have a single initial state. And then we're going to, for each episode, we're going to run it for a finite number of steps. Okay, and so you'll terminate after that number of steps. And this is just for mathematical convenience in writing things down in our notation. And we're not going to consider any discounting, but it's very easily incorporated. It's easier just to not have to worry about that. And we'll let this rho theta function represent the expected value of the policy, pi theta. So the theta is a critical thing. When we fix theta, we fix the policy. Rho theta is the expected value of the policy from that initial state. So if you run the policy, a million times from that initial state, and you average the total reward it got, that's what rho theta is, basically. Okay? And we want to find the parameters that maximize rho theta. Right? And so what I just told you should be relatively simple, right? All we do is we compute the gradient of rho theta, and we move the parameters in that direction. But there's a big problem here, right? Rho theta is not a nice little function that we can compute the gradient of, right? So neural networks are not nice little functions either, but it's just a feed-forward circuit, and it's very easy to sort of back-propagate to get the gradient. Rho theta is a complicated thing. This is the process of the expected value of possible trajectories that this policy could compute. And there's no closed form for that function, and there's no closed form for the gradient, like the exact gradient that you can get easily. So we're not going to be able to analytically compute the gradient, basically. That's a problem. If you want to try yourself, you can try to do this, but it's pretty. You're not going to be able to do it. We'll see the policy gradient theorem later that gives you some ways to approximate it, and that's what most of these policy gradient algorithms are going to be based on. So the key idea is, instead of analytically computing the gradient, we're going to use experience to estimate the gradient. Okay? And if we're lucky, our estimates might be unbiased estimates, so that as you get more and more experience, you get closer and closer to the true gradient. And so that's a key idea behind policy-based policy search algorithms. So we're going to run into one problem first. So this way of defining a policy of computing the max over this H function, this action scoring function, that's inherently a discontinuous policy, right? In the sense that if you change theta, you're not necessarily going to get you could get a sharp change in the policy selection. I guess talking about the continuity of this function doesn't make sense. What we want to talk about is the continuity of the value of that policy, right? So gradient descent tends to work best if you have nice continuous functions, right? When it can really screw up is, and it can screw up in other ways, but when you have functions that will be up here and then all of a sudden be down here, like a discontinuous change, that can be really confusing to gradient descent algorithms and cause them to go bonkers, because they can end up in places that they can't recover from. So the question here is, if we represent our policy this way, is rho theta, the value of that policy from the initial state, going to be continuous? What do people think? Necessarily? No? Yeah, so why not? Anybody have some intuition about why not? Or can you give an example?
Probably do the maths here. It'll make it discontinuous.
So it feels like, yeah, if you... what's up?
If you put a smooth thing, like the max, give max.
Yeah, so the policy certainly for there are going to be values of theta that an epsilon change will cause the policy to change, right? That's just what's going to happen. And if the policy changes all of a sudden with an epsilon change in theta, the value can change. And this is just the most simple example to show that, to illustrate that. So we get a very simple MDP here. So S0 is the start state. It's just a one-step thing. You take action A, probability 1, you get a reward of 100. Take action B, probability 1, you get a reward of negative 100. Right? So obviously the optimal policy is A here. If we're using some representation like this, we can, so our policy now, we have two features, theta 1 and theta 2 are weighting these values. And we can consider fixing theta 2 while we vary theta 1. And it might look like something like this, right? This is all just fictitious, but it's going to be some linear function of theta 1, right? And you can see at this point here, this is where, so what we're plotting here is the line, the score for action A and the score for action B. And at this point here, this is where the policy changes, right? Because as theta 1 was over here, we would take action A. Over here, action B starts to win, right? And it could very easily, and basically what happens is on this side of that threshold, the value is going to be 100. On this side, it's going to be negative 100. So you get this discontinuous change. So this is basically a simple example that shows you how discontinuities can happen in your value function when you have these deterministic policies. Okay? And the reason that we might not like them is because this can, if you're doing gradient descent, this can really screw things up. It is true that people do gradient descent all the time on discontinuous functions. It tends not to be, so they'll use subgradients, and it tends not to be a big problem if it's discontinuous in like a ReLU type way. So ReLU functions are more like something like this. It's not like you're going from here to here. So this is a very different type of discontinuity compared with this. That's why this type of discontinuity is sort of not so good for us. So what we're going to do is we're going to move away from deterministic policies. And instead, we're going to start working with probabilistic policies that output distributions over actions instead of just outputting a single action. Right? And that's going to be our way to try to get more continuous functions to work with. So a probabilistic policy, pi theta, just takes a state and an action as input and returns a probability of taking that action, right? So the sum of the probabilities over A have to be 1, right? And so given a probabilistic policy, you can just sample an action from that policy, and you would take that action online. Now the important thing is that when what we're going to want and what you typically use is when you change theta, the probabilities are going to change continuously. And that's sort of so you're going to change from taking A with some probability to taking A with less probability, but B's probability will go up a little bit. And a typical way of doing this is to define a softmax function or a Boltzmann exploration function. And this would be a way of representing your policy. So we have our scoring function, but now we're putting it inside sort of a probability function. And we've already seen how this sort of converts scores to probabilities before. We're not having the temperature parameter there. You can say that that's kind of baked into H. Like if you multiply H by a constant, it's like multiplying it by a temperature. And so this is a common way of defining policies that you'll see very often. And now our same example, we don't really need to work through the details, but what you get is that the value for this problem here is equal to this expression. So it's 2 times the probability assigned to action A minus 1 times 100. And now if we consider the same problem, this is what you're going to see. It's going to be a more continuous function. And intuitively, yeah, right here, it's like 50% chance of taking action A versus action B. And so you're getting sort of 0 reward right in the middle on average. So that's your expectation. All right, so any questions about continuous, these probabilistic policies? They're very common in policy-based optimization. So although there are more and more algorithms now that are trying to do policy search with deterministic policies for certain reasons, but this is very common. All right, so what we're going to do, I'm going to show you the first simple thing that you can always try if you have a pretty small parameter space. So if you have a little controller that maybe you had a small number of features and you think they're sufficient to define a softmax policy, a very simple thing to do is empirical gradient estimation. And everything that we do after this is going to be to try to improve on this. So if we remember what the gradient, this is sort of a brain dead thing to do, but it can work for you when you have the resources. So remember the gradient is just, well, I'm going to tweak parameter I, right? Tweak it by a little bit, divide by epsilon, and then that's the limit as epsilon goes to 0. So empirical gradient is just doing this, but for a very small epsilon. So you just compute this difference for a small epsilon and you divide by epsilon. And there's a whole literature on how do you do empirical gradient estimation. Like you might get 2 measurements, epsilon, on each side of theta, and average those. But this is just a very simple way of doing it. So this would be an estimate of the gradient. And you can do this for every parameter, right? And so you just say, okay, I'm going to tweak each parameter, and I'm going to see if it makes the value go up or down. And then I'm going to move the parameter in that direction. Right? That's all this is saying. The fancy way of saying that is empirical gradient estimation. And so what we have to estimate is, if we want to get all of the gradients for all of the parameters, you have to estimate, well, first you have to estimate this. How can we estimate this value from experience? The rho theta. If I give you theta, how do you estimate it from experience? Not a trick question. Right, I'm giving you a policy. How do you estimate the value of the policy?
It's average.
Just average. Run it some number of times. Average the values that it gets. Right? And same thing here. For each of these ways of tweaking the parameter, you can run it some number of times, and you get the estimate of the value. Right? So this would require some number of trajectories. I guess we're talking about that. So this is how you visualize it, right? We're going to run the original policy for n times, run the tweaked version n times, this tweaked version n times, and that's how much experience you need. So if there are little n parameters in big N episodes to estimate each one, you're going to have little n times n, big N episodes that you have to run. And so that could get expensive, right? This is a lot of experience. Can be done parallel. You can parallelize this very easily, right? This would be a nice thing to parallelize with Ray because these are completely independent. And so that's all we really have to say there. So that gives you a gradient estimate. You get your estimate, then you would move the parameters, and then you do this thing all over again. Okay. So it's pretty expensive, but if you've got the resources and you've got a small enough number of parameters, this can work. But if you have a giant number of parameters, like a big neural network with thousands of weights, you're not going to want to do it this way, right? You're not going to want to change each weight by a little bit and then run the policy over and over. So we need some other way of doing this. All right, so the big thing about what I just showed you is a black box approach. It doesn't actually care that we were adjusting the parameters of a Markov decision process. Instead, it just looked at the empirical returns and ignored all of those facts. So what we'll do next time is, well, since we know we've got the policy of a particular form and we're running in a Markov decision process, there must be some better way of computing the gradients. And we're going to show how to, if I give you a policy of a particular form, just running that policy, you're going to be able to compute the gradient vector without actually tweaking the parameters and running the policy again. Right? And so that's going to be a very powerful thing. So just running your current policy, you're going to be able to estimate the gradient just from those trajectories. And we'll show how to do that next time.